Imagine a star, many times more massive than our own sun, living out its magnificent fiery life for billions of years. It fuses elements in its core, creating the very stuff of which we are made. But all stars, no matter how grand, eventually run out of fuel. For the most massive ones, the end is not a quiet fade but a spectacular collapse. Its own gravity, an unstoppable force, crushes the star's core down, 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 into an infinitely dense point, a singularity. This event creates an object so extreme, so gravitationally powerful, that nothing, not even light, can escape its grasp. It's a region of space-time that has been warped to its absolute limit, a cosmic abyss from which there is no return. The boundary of this one-way trip is called the event horizon. Think of it as the brink of a cosmic waterfall. Once you cross it, you're going over the edge. Inside this horizon, the laws of physics as we know them seem to break down, and the singularity at the center remains one of the greatest mysteries in all of science. We can't see inside a black hole because the light that would carry information about its interior can never get out to reach our telescopes. According to our best theories, once matter falls in, the black hole only remembers three things: its total mass, its electric charge, and its angular momentum, or how fast it's spinning. Let's talk about information. Not just the words in a book or the data on a hard drive, but the fundamental information that describes every particle in the universe. In physics, information is everything. It's the unique identity of an electron, its position, its velocity, its spin. It's the arrangement of atoms in your DNA. Information can never ever be truly destroyed. You can burn a book. The information isn't gone. It's scrambled into the smoke, the ash, the heat. If you could collect every particle, you could piece the story back together. Now bring back our black hole. Split screen, general relativity versus quantum mechanics. General relativity describes the very large and black holes perfectly. Quantum mechanics insists information is eternal. Black holes force them to meet and they don't agree. This clash gives the black hole information paradox. What happens to the information of things that fall into a black hole? According to Einstein, it's gone forever, trapped behind the event horizon. One theory says wiped clean, the other says preserved. They can't both be right. For a long time we thought black holes were truly black, eternal cosmic prisons. They only ever grew, never shrank. In 1974, Stephen Hawking did calculations trying to unite quantum mechanics and black holes. He studied particles near the event horizon and stumbled on something extraordinary. The vacuum of space is a fizzing soup of virtual particles, pairs that usually annihilate immediately. But if a pair forms at the event horizon, one can fall in and its partner can escape. The escaping particle can't annihilate its partner, so it becomes real. To an outside observer, it looks like the black hole spat something out. That requires energy, taken from the black hole. The particle falling in carries negative energy relative to the escaping one, so the black hole loses a tiny bit of mass. Over mind-bogglingly long times, this slow leak makes the black hole lose weight. It shrinks and eventually evaporates in a final flash. Hawking's calculations showed the outgoing radiation is purely thermal, random. It contains no information about what fell in. A black hole formed from a collapsed star would radiate identically to one formed from a trillion encyclopedias. Unique identities and stories appear erased. Why do physicists get so worked up about losing a little bit of information in a black hole? Because the principle of information conservation isn't just a neat idea. It's the foundation upon which much of modern physics is built. It's a property known as unitarity in quantum mechanics. The evolution of the wave function is reversible in principle. Think of it like a movie. If you have a frame and the rules, you can play it forward or rewind it to see the beginning. But if information is destroyed in a black hole, it's like someone cut a scene out of the film and burned it. You can no longer rewind back to the beginning. The chain of cause and effect is broken. The past becomes fundamentally unknowable. The universe would be unpredictable at its most basic level. This would unravel cherished concepts in science, the conservation of energy and predictability itself. It would inject a terrifying randomness into the heart of reality, a crisis for the logic we expect from the cosmos. We have a choice. Either Hawking's calculation is missing something, or one of the pillars of physics is wrong. Do we abandon quantum mechanics, the stuff behind your smartphone and chemistry? Or do we challenge Einstein's gravity at the event horizon? Physicists would rather do almost anything than give up on information conservation. Once Stephen Hawking declared that information was destroyed, the physics community split into camps. Each proposed a different fate for the universe's lost and found department. The simplest and most terrifying answer was that the information is truly lost forever, gone. Hawking's radiation looked thermal and random, but what if there were subtle, incredibly faint correlations hidden in the outgoing radiation? Imagine burning a diary. The smoke and ash seem random, but in principle the words are encoded in the precise state of every particle. Maybe Hawking radiation works similarly. The object's information is slowly imprinted onto escaping particles, scrambled beyond recognition but not destroyed. Then came even more exotic proposals. One idea: the information doesn't come out but isn't destroyed. It's stored inside a tiny remnant when evaporation stops. What's left is a small nugget holding all the data. But remnants bring problems. There should be countless strange nuggets in the universe, yet we see no evidence. Another branch ventures into baby universes. Perhaps the singularity is a gateway that pinches off a new universe, carrying the information away. Poetic, but inaccessible to us. Like remnants, these ideas are currently untestable, on the speculative edge of science. The information paradox sparked a famous wager. On one side, Stephen Hawking and Kip Thorne argued information was destroyed. On the other, John Preskill insisted it was preserved. The stakes: an encyclopedia of the winner's choice, a symbolic bet about retrievability of information. Hawking and Thorne believed gravity was absolute. Once you cross the horizon, the game is over. Information crushed at the singularity. Preskill placed his faith in the unshakable foundations of quantum theory. Giving up information conservation would be a bridge too far. Then in 2004, at a conference in Dublin, Hawking stunned the community. "I have solved the information paradox, and the information is not lost." His new thinking was inspired by ideas like the holographic principle, suggesting information could be encoded at the boundary of space. He presented John Preskill with a baseball encyclopedia, a symbolic concession that information might be retrievable. Hawking admitted the universe seemed not as forgetful as he once thought, but the debate far from ended. Researchers continued to argue about mechanisms that could return the information. The key insight came from Don Page, the Page curve, a prediction for how entropy of Hawking radiation should change if evaporation is unitary. He thought about the black hole and its radiation as one entangled system. At first, the radiation's entropy increases. Early emissions look random and entangled with the interior. Around the Page time, roughly halfway through evaporation, the trend should reverse. The radiation becomes more orderly and starts to carry the original information back. Think of normal burning. The smoke initially entangles with the coal, but in the end, the smoke contains the information. The Page curve is the signature of that behavior. Hawking's original calculation predicted entropy that only grows, which implies information loss. Page predicted a rise then fall if unitarity holds. In 2019, a series of papers showed how, in certain models using holographic tools, one can compute the entropy and reproduce the Page curve. This was the strongest evidence yet that information escapes. But the math didn't fully reveal the physical mechanism. The how remained mysterious. Deriving the Page curve is widely seen as progress toward resolving the paradox. If information gets out, outgoing particles must be correlated with earlier radiation and with interior partners. But quantum mechanics forbids a particle from being fully entangled with two different systems. Monogamy of entanglement. One proposed fix: a firewall. A blazing wall at the horizon that breaks entanglement and preserves quantum mechanics, but would incinerate anything falling in and violate Einstein's equivalence principle. String theory offers another idea: fuzzballs. Instead of an empty horizon, the black hole is a tangled ball of strings with structure at the would-be horizon. Matter hitting the fuzzball becomes complex vibrations that radiate, encoding the information. No true horizon, no singularity. Another suggestion: soft hair, low-energy photons and gravitons that store information at the boundary. It's intriguing but limited to certain space-time conditions. A different route: strong quantum effects at the end of evaporation leave a remnant that holds information. This avoids early breakdown but raises other paradoxes about storage capacity and unobserved remnants. A minority view accepts information loss and modified quantum mechanics. Thinkers like Penrose argue non-unitary processes could occur with gravity. These ideas are speculative and have testable consequences debated in the literature. Other proposals include final state boundary conditions, baby universes, or encoding and correlations across time, all active areas of theoretical exploration. After decades of debate, we are in a thrilling, confusing, and incredibly exciting place. The discovery of the Page curve convinced many physicists that information is saved, But the how remains a battlefield of ideas. Solving the paradox forces us to invent new physics, a quantum theory of gravity that unites Einstein with the quantum rules of the small. A black hole is a laboratory created by nature itself, letting us test ideas we can't replicate on Earth. This is a story of brilliant insights, stubborn paradoxes, public bets, and slow, painstaking progress built over generations. A new generation of physicists keeps pushing, calculating, imagining. We are listening to whispers from the edge of space-time, trying to decode a message about the fundamental nature of reality, information, and even time itself. The black hole information paradox isn't a dead end, it's a gateway. It's a promise that there are still incredible, mind-blowing discoveries waiting for us out there in the dark. In short, Hawking revealed black holes radiate. Hawking's original result suggested information loss. Page predicted a unitary page curve. Recent calculations reproduced that curve, suggesting information is preserved. But how remains an open and thrilling question. If you want to dive deeper, look up Don Page, Stephen Hawking, the holographic principle, and the 2019 entropy papers that derived the page curve. This remains active research. Theories clash, calculations evolve, and experiments and thought experiments continue to sharpen our picture. If you enjoyed this explainer, like and subscribe for more deep dives into physics. Links and references are in the description. Thanks for watching. Special thanks to the researchers whose work shapes this mystery. See you next time.